In 1872, the British research vessel HMS Challenger spent 4 years mapping the ocean floor, using hundreds of pounds of lead weight and rope. Off the island of Guam, their sounding weight dropped further than anyone thought possible. To understand the sheer scale of the depth they uncovered, we can look at Mount Everest. If you placed the world's tallest peak at the bottom of this abyss, its summit would be submerged under more than a mile of water. Detailed topological maps reveal a jagged scar stretching 1,500 miles across the Pacific floor. Near the southern end of this system, the floor drops even further. This is the Challenger Deep, the lowest known location on the planet, resting nearly 36,000 feet below the surface. Understanding this space requires abandoning our surface-level intuition. This is an environment governed by extreme verticality. The trench exists because of subduction. For millions of years, the massive Pacific Plate has slowly ground beneath the Mariana Plate, forcing the crust downward. This immense depth introduces extreme hydrostatic pressure. Because water has mass, the weight of the water column pushing down from above scales exponentially the deeper you go. At the floor of the Challenger Deep, that water exerts 16,000 pounds of force per square inch. This force acts isotropically, meaning it crushes inward equally from every possible direction. That is 1,000 times greater than the atmospheric pressure we experience at sea level. It is the equivalent of stacking dozens of jumbo jets on a single human body. To survive this abyss, any biological or engineered system must solve this 16,000 psi problem. Historically, this has forced two divergent paths of design: absolute rigidity or absolute compliance. In 1960, humanity attempted to conquer the trench using brute force material science. This was the Trieste.
To protect a human crew, engineers built a tiny cabin enclosed in steel walls exactly 5 inches thick. They used a spear because it's the optimal geometry for distributing isotropic pressure. Flat sides or cylindrical edges would concentrate the inward force, causing immediate structural collapse. But extreme pressure created a secondary problem: buoyancy. Standard submarine ballast tanks filled with air would instantly implode at 16,000 psi. Instead, the Trieste suspended its cabin beneath a 50-foot outer hull filled with aviation gasoline. Gasoline is lighter than water, providing lift, but as a liquid, it structurally resists extreme compression. Don Walsh and Jacques Piccard physically tested this model, sealing themselves inside the tiny steel sphere. This first intrusion into the deep relied entirely on fighting the ocean, using heavy engineering to hold the crushing weight at bay. During their 5-hour descent into the twilight zone, the escalating pressure placed immense structural strain on every square inch of the vessel. At 20,000 feet, the mission met a critical failure point. The immense weight caused the Trieste's outer glass window pane to violently crack. Walsh and Piccard survived, but modern descents mitigate that catastrophic risk. When James Cameron dove to the trench in 2012, his vessel utilized advanced synthetics and composites to handle the extreme loads safely. Today, researchers primarily use remote-operated vehicles equipped with specialized floodlights and heavy housings to map these zones without risking human life. Rigid engineering is highly effective, but a cracked pane or failed seal results in instant destruction. To see how to truly survive in this extreme environment, scientists had to look at how nature solved the exact same problem. The biological alternative to heavy steel is absolute compliance. Deep-sea organisms survive extreme pressures by eliminating air-filled cavities entirely. Their tissues and internal systems are perfectly equalized with the surrounding water pressure, allow them to easily maintain internal equilibrium. The transparent deep-sea squid is a prime example of this fluid statics engineering. Where the Trieste relied on rigid walls to deflect and block the inward force, nature allows the crushing weight to pass harmlessly directly through the fluid-filled structure of the squid. Vertebrates use a similar strategy. The Mariana snailfish evolved a specialized, hyper-flexible skeleton that bends rather than breaks, preventing structural collapse at maximum depths. Because these depths are completely devoid of sunlight, secondary adaptations are required. Predators like the anglerfish generate their own bioluminescence for hunting and communication in the absolute dark. Evolutionary biology solved the 16,000 psi problem not by resisting the ocean's immense weight, but by becoming completely one with it.
Pressure is only half the equation. The abyss is also defined by a permanent disconnect from solar energy. Photosynthesis is physically impossible here, meaning the ecosystem requires an alternative method to deliver calories. Survival at the bottom of the world relies entirely on a gravity-fed energy pipeline. This is marine snow, the constant slow-motion gravitational transport of organic particulate matter, detritus, and carbon sinking from the upper ocean to the organisms waiting below. The trench exists in total solar isolation, yet gravity permanently tethers its survival to the biological cycles occurring thousands of meters above. When Walsh and Pickard finally reached the seafloor in 1960, they observed a bottom-dwelling flatfish. That single sighting proved the high-pressure trench was not a sterile, lifeless vacuum. But there is a dark side. The exact same mechanism delivering life-sustaining organic snow is now indiscriminately transporting human waste. Expeditions have verified undeniable traces of pollution, including plastic bags and industrial chemicals, resting at the absolute bottom of the Challenger Deep. Tectonic subduction and gravity make the Mariana Trench the final destination for Earth's surface systems, proving the deepest point on the planet remains linked to our own actions.